Okay, let's start. Sorry for the delay because I wanted to be modern with these things and I didn't charge it. So anyway, so the only step we did in some sense it was to talk about this way of representing the momentum in a matrix. We're calling P. That is a 2 by 2 matrix, okay? And we were saying this can be written as a function of two spinors, okay? And we got into this definition. If there's a particle that I label with 1, we put the 1 here, okay? And you can talk about the spinors. I mean, there is a, if you give me the spinors, you give me the momenta, okay? And to make it clear, for example, if you want to see an example, if I get the P mu of a particle moving in the x direction, E00 E, okay, the P, the matrix, we put a bar here, down here to make it clear as a matrix, is in this case, okay, so we can talk about this P or you can talk about this matrix P, okay, this could be 2E000, okay, following the definition I gave it to you. And if you want to go to the spinors, the spinor will be 10 square root of 2E, okay, and the other will be also 10 square root of 2E, okay. So again, it's a different way to give the momenta. Okay, give me the spinors, you give the momenta. You can check this is working with your definitions, okay, that you plug it in, and in some sense will help me already because you have to remember these spinors have dimension of square root of energy. Okay. Now, if the momenta is real, as is in the real world, okay, you get the conditions, okay, that this guy has to be the complex conjugate of this guy. Okay, so if the P mu is real, okay, you will say always is real. Okay, this guy has to be related with the other. But I don't want to talk much about this because we will remove the condition of being real. Okay, this is a big step we're going to take. Okay, this has to be the complex conjugated, okay, of this guy. But we are going to move, and this implies that this P must be Hermitian. Okay, you can just check it. I don't want to enter much into the real because it has to be an important point to go to the complex momenta. Okay, so be prepared for this, but okay. So physicists, we have done many times already, jumping to the complex plane, okay, and back to the real plane at some point, okay, to do physics, okay. It will be very important. It's the crucial point to do the complex momenta. It's an amazing thing. We couldn't do this thing without this, and this is why it took some time, okay? So now we want to do the amplitudes, and we want to do built amplitudes with these objects that are spinors, okay? So the question is, instead of talking about, you see, amplitudes, as you know, products of P1, P2, okay? Okay, P1, P mu, okay, as you do always, you write this Lorentz invariant. So since we want to write it as a function of the spinors, okay, now this in spinors. So we have to write it, of course, that there is, in the same way you contract the mu's, here you have to contract the alphas, okay, that is your Lorentz index, okay. And because have to remember these are spinor of that under Lorentz transform as with the M was defining under Lorentz transform as the spinor goes to M, a matrix of 2 by 2 complex matrix of determinant 1 acting on the spinor. This is the Lorentz group in this SL2C, okay, and its determinant 1 we can make as invariant by contracting with the epsilon. Okay, if your matrix the transformation is of determinant 1, contracting with epsilon, you get an invariant, okay? So we'll write invariants, okay? Right now I keep the alpha and beta, and it's a nightmare called keeping them, and at some point I'll drop them, and we can forget about them, okay? But right now they keep it, so I can contract these two spinors with an epsilon, and this is a Lorentz invariant, okay? Now we're going to define this thing, exactly this thing. Sorry, I'm going to take 1 and 2, because otherwise it would be 0. Okay, so I'm going to contract with labeling different particles, the particle 1 and particle 2. Okay, otherwise it's 0, of course. It's contracted with epsilon, it would be symmetric. Okay, like this is going to property. Okay, and we call this like this, 1, 2. Okay, that is called the angle bracket. We will call it like this. Okay, and similarly, we're going to contract the complex spinor alpha dot. Okay, I'm going to write it like this. Okay, and we'll call it square bracket. Okay, of course, don't get confused with quantum mechanics. Okay, there will be other brackets, or states will also have the brackets of quantum mechanics. Okay, but this is the notation people. Is the name people use it. Okay, and this is the notation people use it. Okay, you get confused at some point. You can go back to your definitions and keep the alphas and betas. Okay, but this is exactly what you don't want to go to. They keep the alphas and betas because you go very slowly. Okay, so you want to talk about this invariance. Okay, so in some sense, your amplitude. Okay, you would like to write it as a function of this 1, 2, or 1, 2. Okay, this is the point. Okay, and you see already the connection what we had with when I put the amplitude of gravity. Okay, that were appearing these guys. Okay, instead of the momenta or the polarizations that you see in field theory. Okay, sometimes you can also use this. Usually we also use the epsilon as we do often, to write it as a lowering on moving up and moving down the indices. Okay, so you can define like this is the complex spinor where the index goes up. Okay, and similarly here you can in some sense when you move when you move up the index, I move also I put the decade as a bra. Okay, sorry this is to make it easy afterwards, because I contract the 1 and 2 in this way. Okay, so this is notation. Okay, that you can pay attention a little bit to be sure what you're doing, but at some point now we forget that these are the important ingredients, and I don't have to go through the details. Well, I probably have to go once more with I will go with the indices detail, okay, to show that we sometimes will contract it with a sigma mu. Okay, and now I can define this guy with the index alpha already upstairs. I already defined it here. We multiply by the sigma mu, we already defined it with these two. Okay, alpha dot up here, okay, because of this definition. Okay, now it's contracted on the indices, it's Lorentz invariant. Okay, and we define this like we want to sigma mu 2. Okay, and we will see these guys like this. Okay, for example, when we multiply with the momentum, P mu. Okay, we will write this. Momentum can go inside, of course. This is the for momentum. This is, we can write it like 1, P2. Okay, we will write in things like this. Okay. This point goes inside here, and I call it P. Okay, and you have to remember this is my this P is my. I'm going to put this is my matrix P. Okay, I can put it now here, but I will not put it anymore. Otherwise, I usually forget. Okay, so this in some sense this is the matrix. Okay, and in fact, let me do it. If I use this definition I have originally there. Okay, that would be also important to write it as a 1. Okay, if I write this guy like P, state of momenta P, alpha P alpha dot, this is 1P, I can write it like this, 2P, sorry, P2. And that would be important because when we do, for example, you see that when you put inside this P, well, okay, let me go slowly to the properties of this thing. Let me show them, and after that we can see the properties that we will be using. Okay, another one is the first, what brings to the first contraction. That is this property of the sigma mu sigma mu matrices. Again, I put the alphas and betas, and again, and at some point I will drop them. Okay. Sigma mu sum over mu's. Okay. For different elements can be of this property. This allows us to recognize this thing that usually you write in your amplitudes P mu P2 contracted, or it's contracted. Okay, you can just plug. Okay, sorry. Before this, let me. We also give that. Okay, from here. Also, if you want to know the components, P mu already wrote this or not? No, I think I didn't write it. The momentum of the I don't know, say particle 1. Okay, you can also write it like this: 1 sigma mu 1. Yeah, you can see probably you need to use this, yes. You need to use this to get it here. Yeah, you have to. Let me see how it goes. You multiply by. Sorry. Yeah? Here? Yes. Information of? This is the momentum of the particle 1. Okay. Let me call it P1. So the components of the P1 for vector can be gotten from here, okay? Of course, the information is in the spinor. In some sense, this is inverting this relation, okay? I want to extract, okay, in fact, I have to go here, yes, okay? If I multiply by sigma mu, I can get back to this thing here. Let me write this one, and probably will be more clear. Okay, P1, P2. Okay, this is using this thing. Okay, okay. If I use this one, okay, this is okay. When you multiply those P mu to have sigmas mu's, okay, and you get quarter 1 sigma mu 1 2 sigma mu 2 this will be important, okay, using this property. And will be in general. Okay, when we have a contraction of some momentum of particle, this will be an important one. Pi Pj mu, okay. I'll write it like this, okay. We have a rewriting of things, okay. I have a rewriting of all the invariant that I can have. Okay, this is the momentum pi with the momentum of the momentum of the particle I with the momentum of the particle j. Okay, contracted. You write it in this way. Okay. Yeah, probably. Sorry, I don't know if this is a question. There is the property that we use 1, 2 is minus 2, 1. I don't know if this was your question. Okay. That of course is because it's contracted with epsilon. Okay, make it clear that this is like a spinors, but they don't anti-commute. Okay, I said probably that when you talk about fields, you have spinors that are also fields or operators. Okay, when they're operators in quantum physics, quantum mechanics, you're forced to make them anti-commuting. Okay, that property of anti-commuting is because you want to be fermions. At some point here are spinors. It means that they transform in a proper way. Okay, but they don't commute. Here they anti-commute because contacted with epsilon. Okay, you exchange 1 and 2. Okay, you're exchanging alpha and beta. You can go back to exchanging alpha and beta, and you have a sign. Okay. So this property is important, in the same, of course, for the other one. But this is very important because it tells you that when you have indices that are the same, like II, this is 0. This is a very important property, okay? You cannot repeat the index inside the, okay, it is obvious, no? From here again, epsilon is antisymmetric. If you put the same index, 1, 1, same particle, is symmetric, antisymmetric, you make it 0. Okay. And I already probably discussed here, but when you have the momentum of the particle 1 acting on 1, this is a kind of okay, let's do it. P1, I use the definition, P1 again, definition there. Similar I use here. And I get I get this is 1, 1, 1. Now this is 0. This is kind of the Dirac equation, but it's not Dirac because we're not talking about fields, okay? But P on the spinor is 0. When we talk about this, if we go to really fermions at some point to describe theory of fermions, this will be equivalent as you do with the V and the U in quantum field theories, okay? This polarization vectors V and U will play a role of these guys, okay? Reacting on them are 0, okay? Here you can forget the moment because at some point this will be associated with particles with spin higher than a half, okay? And the same you can do for if you act from the other side. Okay, you can do it for you and get 0. There are many few properties important. I don't know if to which one to give you. Let me see. Okay, there is this. You can see there is a condition that could be like a momentum conservation. Is that if you do this, this is like AI summing of over the momenta of all particles in a process. Okay, you sum over all the states in an amplitude. This is this. Momentum conservation tells you that this is the sum of the all momenta incoming, and we will be talking all the time. Right here, I start putting some convention and definition. Okay, one is the momenta, always is incoming. We'll consider this. Okay. And there's another, yeah, okay, probably another. Yeah, also the first relation, this first contraction, this property of matrices also give you the, okay, using this, give you also more generic than before is, then you can check if you have this thing. This is -2. To 4. You see, if I need the property, I think I will come back to give it to you, okay? Because if I start giving properties, I don't know, I will not stop. Okay, and I want to move to the second important step, okay? You understand that now because these are my guys, okay? Okay, these are my amplitudes. I'm saying all the time, I'm going to be written in this with these guys, okay? You see, you're very used to do it with p mu's and all the combination here and how it works here. And now you have to develop a little bit of, okay, what can you do here to manipulate and to write it simple, okay? And these guys are probably not used to it, okay? So these properties, for example, when you see this index contracted equal 0 or things like that, and okay, and different properties, okay? There are other ones, when I need it, I'll bring it up. I think it's better like this than giving it to you. The important point is that we are not going to put, okay, alphas and beta anymore. Somebody's confused, even myself, when I'm confused, I go to alpha and betas, okay? Back to put them to see that I don't miss any sign, okay? But this would be a trick, okay? To write it like this, to write this like this, okay? And Now, in some sense, you can be, okay, you can follow more or less these things, okay, because P is the contraction with the alpha, so you follow these things, and okay, not much so far. So but now we want to see. Now we want to see that the amplitudes when written with these guys, okay, going to be very simple because there are two things more you need to write amplitudes, okay, in a simple way, and the two things is will give you the constraints of how these guys can appear. So the point will be that the amplitude as a function of this guy is going to be very constraining, so much constraining that you will be able to derive it from the constraints. Okay, people sometimes call it the bootstrapping away. Okay, so you have this constraint, and now when you look at the amplitudes, you can derive it. Sometimes you do it in 2 seconds, sometimes it looks like 5 minutes, but that's much less than going through Feynman diagrams. Okay, okay, this is the key point. And before that, we need two still important properties, that is dimensional analysis and the little group. Okay, transformation, because it tells you how these spinors must appear, okay? I don't know how familiar you are with the little group. Is the usual way you define your states in quantum mechanics, okay? Have a clear transformations under Lorentz, okay? And the little group is exactly the subgroup of the Lorentz group that lives invariant. If you have a particle momentum P, okay, we are taking massless states, is the one that, okay, rotation that does not change the momenta, okay? This is a subgroup of them. In the case of, I don't want to enter too much, okay? In the case of massless particles, this is the ISO2 group, but it doesn't matter. The important point is you can always, is the subgroup of this ISO2, that is the fact that you can do, in a particle momentum P, you can always rotate in that direction. Okay, of course you cannot rotate in that direction, but any rotation, okay, in that direction, okay, using this, around this axis, sorry, any rotation around this axis leaves invariant, of course, the momentum, the particle, okay. The extra things in the little group, I don't need them, okay. In some sense, this is the rotation. The only thing I need is the rotation around the p-axis of a state. Okay. And when you, and on the state, what it does, okay, is the way you define velocities, okay, the states must be states with eigenvalues, okay, the group is a U1, it's a rotation, it's also 2, okay, it is the same as the U1, okay, and the mass transform is in the way we define the velocities, the eigenvalues of the okay, values of the different charges of U1 of this U1, okay? Okay, and define the helicity of the state, okay? And in the amplitudes, is on the state, on the amplitude, okay, I define, I think, the amplitude. Let me see my definition. I don't know if it will be crucial, but I'll write it here. I think was, I don't know, since Rodrigo already used it, but I'm not 100% sure. I saw the same, okay? So I'm going to take T out in a state in an amplitude, okay? We do the bracket. you write it like 2 pi to the 4, now die. iPad die, okay. I don't know if you, okay, this is 2 pi to the 4 delta 4, okay, the sum over P of the inner states I forgot how it was parameterizing, okay? This is a delta function of the, okay, the delta function of the conservation of momenta, okay? You're right. Very good, thank you. Yeah, I have it. Okay, times M, and this is the times A, okay. Okay, this is my amplitude. The definition of my, I think is the, okay. Okay, so the amplitude is made of brackets, I mean, sandwiching the T matrix, the T operator into the in and out state. So, so under this little group, the amplitude is not invariant. It changes a shape, a phase. Okay, that's a key point. Okay, so the amplitude is invariant. So it's covariant in this case. Okay, so it's up to a phase, but that doesn't matter a total phase. Okay, but this is an important property to remember. If I have a, okay, this is for if I have a particle here of, yeah, probably go to the notes. Okay, sorry, let me go. Did we print it? No. I don't want to start with the notation. Okay, what I can do, meanwhile, I can talk about the, what is the little group is the rotation that leaves this guy momentum invariant, and I can think how acts, how the spinors transform. It's very simple here. I have to do a transformation that leaves this invariant. So I can change the phase here of this guy as soon as this guy transforms with the conjugate of the phase. Okay? This will leave the product always invariant. So there is a redundancy in these spinors. If you want, there's more. It's a okay. So in some sense, they will transform as you would expect from a spinor, okay, and yeah, yeah, okay. So the states are defined, okay, as the state from the Lorentz group are defined by the momentum they have. Okay, sorry, don't put P here. Okay, you can put it or not, doesn't matter. Sorry, you have to put it not to be confused with many P's. Okay, by the three momenta. Okay, when you fix the three momenta, is also the energy fix, and the polarization. Okay. Okay, and yeah, you have to remember this from how you were defining your states in a Lorentz invariant theory. This is the big trick of to get this unitary representation. Yeah, it's a little bit more complicated than how transform fields, because you have to look for unitary transformations. You do transformation of fields, you don't need to be unitary. And yeah, sorry if this is important thing of the Lorentz group, but I don't know. We can chat later, but otherwise we have the turn. So lambda is the polar, okay, helicity, sorry. Yeah, thank you. Yeah, say it by word, okay.
but you're
okay.
trying, someone
Okay.
went.
Changing, okay. And if it's, sorry? If it's locked, I have to come to you. Okay, what a disaster. Okay, anyway. Yeah, this I have to give it for granted. Okay, yeah, sorry. This is just. I mean, it's in our books of quantum field theory. We can go back to it. Okay, but I have to give it for granted. Okay, that the states are defined by give me the momenta of the state and the helicity of the state, the massless state. Okay, this is the way I characterize the state. Okay, and the only thing I need is how to transform this little group. That is a transformation. That is a rotation. Okay, along the axis of the momenta. This is the trick, okay? This is a U1 symmetry, okay? And this, I characterize in some sense with the charges under this U1, that there are the helicities, okay? Sorry. It's how to characterize, okay? Characterize the theories by according how they transform under this rotation, okay? Okay, the rotation SO2 is the same as U1, okay, and I have to find the different quantum numbers of this U1, okay, this is the U1 transformation, okay. It's a kind of U1 transformation that is the same as SO2, okay, in algebra, and the charge, if you want, of the quantum number under this number under the rotation is what characterizes my states, okay. For different lambda, I can have different states, okay. This has to do with the helicity of the state, okay? I cannot, lambda, I cannot say much why, but it should be quantized, okay? You can see it in different ways, okay, that when you go to 2 pi rotation, you get, okay. Sorry. Sorry? Sorry, yes, plus minus, sorry. Thank you. Sorry. Thank you very much, yes. Perfect.
Then it sounds like the amplitude should be invariant.
Eh?
I mean, if this is the case, then it sounds like the amplitude should be invariant, right? Because you only have like brackets.
Yeah. Exactly. This will be the point. Yeah. When I have these guys contracted, okay, but we'll be contracted with other particles, okay, and each particle will have their own helicity, okay, and this is you're going to have problems all the time. Yeah. No, I cannot do it.
Yeah.
The only thing, if you can tell them not to be blocked.
Yeah, I don't know if that
do
can
it.
be done or not. I think the lock system is.
Let me check if I charge mine. But I have. Yes, at some point, we start keeping real, okay, and at some point will be becoming complex. Yes, we have not gotten to the point, but it doesn't matter. Still, if I want to have a transformation that leaves that thing invariant, okay, still I will have to, okay, one will have to be inverse of the others, okay. So now it's a phase, okay, and complex conjugate, but if it's a, always will have, if the transformation still is defined in the same way, one will have to be inverse of the other, okay. Yeah, sorry. So the amplitude in the case of a particle of helicity, okay, where it involves a particle of, I have a, how to say, okay, particle 1, let me write it like this, it will come like this, okay? And the idea is that this all together give you a constraint. Because the transformation under the little group will have to, if I write the amplitude as a function of this object, will have to be given by these objects. Okay? In another way, I'm looking only at one particle here, not to make a big formula here. So in my amplitude, when written as a function of these spinors, okay, that transform in this way, we have to reproduce this property here. Okay? Okay. And this will be a very important constraint. Let me say it clear, an example. Okay, to make it clear, okay, the formula is probably general. You have a particle 1 with entering with P meant to P1. Okay, it has a licity, let's say lambda 1, 1. Okay, it's like a photon. The photon entering with licity 1. Now, how the amplitudes could look like, okay, the amplitudes will contain these spinors, but we'll have to get combination like this, okay, this is the constraint we'll have. Okay, we have to have this guy, okay, for example, 2 times. This is a possibility, this would be okay. Okay, but each of them transform as a spinor, transform a half, and I have to get in total lambda equal 1, the transformation. Okay, if lambda is equal 1, I have half and half for each spinor here. Okay, so this transforms properly like under this, follows this property. Okay, this follows this property, this also follows this property. Okay, or 1 divided by also follow this property. Of course, I can multiply always by 1, 1, okay? Because when I do the transformation here, this will not change, okay? But I have some information of how many powers must be in the either numerator or denominator, okay? The total number of these spinors, of the angle spinors, have to be 2 of them if they are in the numerator, 2 of them in the denominator, they have to be square spinors of this type, or I can have a combination of one with the other, like this one also, okay? Now you can prove that, okay, if transform this half, okay, e to the minus theta half, e to the minus theta half, it will transform the full amplitude as should transform on the little group, e to the minus theta lambda 1, when lambda 1 here I took it to be 1, okay? Okay, this is one of the very strong conditions that will fix this thing. Okay, this is one of the important. The other one will be much easier. Will be just dimensional analysis. Okay. Okay, it's just to looking at the dimension of the, we have to be looking all the time at the dimension to get the right. Okay, so the idea is we'll be able to construct this amplitude by knowing how the spinors of this type should appear. Okay? You're losing a little bit of the knowledge of what is a spinor here. Probably here you get an intuition. Okay, let me see what are these, not to be completely lost. Okay, if the momentum is real, okay, so this is real. Okay, we already say that this has to be one complex conjugate, one or the other. And you get a feeling that these guys, up to a phase, behave like a square root of P1, P2 contraction. Okay. There's some phases in front that I don't care. Okay, just to get a feeling that when we talk about this bracket, okay, this is the, okay, one is the is related by complex conjugation to the other one. Here I can put exact. Okay, and some sense like if I get that these angle brackets or square brackets are square roots of the contraction of the momentum, P1, P2. To get a little bit of the feeling, because you know how you have a feeling of what the momentum is, but not, you are lost when you talk about, and we are lost a little bit when we talk about these spinor contractions. Anyway, let me go to the dimensions. The amplitude is, as I define it there, is first dimension of energy times 4 minus the number of states. Follow the usual notation that contraction of two states of momentum P at Q, okay, defined with 2E, 2 pi 3, delta 3, P minus Q, okay, so just by looking at this, you know the dimension of the states, and you know the dimension of the amplitude, okay, as defined that is like this, okay, 4 minus n states, probably already you know, for example, the 3-point amplitude, okay, has dimension of energy, okay, and that would be important, okay, to remember, and the 4-point amplitude has dimensions, is dimensionless, okay. That would be important, and also the dimension of these brackets, you have to remember, that is already given there, you can, okay, the dimension of this will be dimension 1, and the dimension, the same thing for the dimension of the IJ is dimension of energy, okay? So when we write this 3-point function, or 4-point function, or 5-point functions, okay, these amplitudes, okay, we have to match with the right energies, okay, so it means I cannot have many spinors in the numerator. If I have many spinors in the numerator, so what is the point, okay? Yes. Huh? Here? Is what the what? Ah, IJ, sorry, yeah, thank you. I think it's working, but okay. I'll put it there charging there. So. Okay, have you? Oh my God, I don't get any place. Sorry, say it again. Yeah, this is PIJ, IJ. Inside the square. Yes. I'm saying this is real, okay, this is back to here, to real, okay? If it's real, this has to be the complex conjugate of this guy, to be real. At some point we will remove this condition, okay? But in our four-dimensional, when we go to physics, my momenta must be real, okay? Our amplitudes are going to go to complex momenta, okay? There will not be real amplitudes in the real world, okay? But at some point we'll go to real momenta. And just to get a feeling of when you write this thing as a function of these spinors, okay, I'm saying, you have to remember that when you see ij in this angle bracket is related with the square root of this thing. But now, okay, the point is that once these two things are fixed, probably the best, and I don't know, I would like to put one example, okay, and we see how we build them, okay, and that's probably the best, okay, that we can do today, okay. It is loading. Okay, so the idea is, these are the all. Okay, so the idea is what we're going to build the amplitudes. Okay, so the basic building blocks, we're going to talk about the first with the 3PT. Okay, and now we're going to take also the idea of effective field theory. Okay, so my amplitude, okay, I'm going to do what is the idea of effective field theory. Here already mentioned is that we're doing an expansion in 1 over lambda. Lambda is the cutoff of the effective field theory. And now, of course, because we'll be talking about this angle bracket or square bracket, this is, of course, is a expansion in momenta. Okay, in our case, will be an expansion in these angle brackets or square brackets over lambda. Okay, this is our effective field theory approach. Okay, we start at first leading order. Okay, so it says lambda to the 0. Okay, order. No lambda appearing. Okay, so I have to write the first amplitude where lambda does not appear. Okay, as in the standard model, lambda does not appear in the standard model. These are the dimension equivalent of the dimension 4 or less operators. And we start with the 3PT, the lowest point amplitude. Okay, and let me do 1. Okay, so amplitude like this one. I'm going to label the particles 1, 2, 3. And we are aiming for the first interaction that would be Yukawa interaction. I'm going to speed up a little bit. We draw it like this, okay? Scalar interacting with two fermions. Okay, and I'm taking elicities here. Let me take minus a half and minus a half. I don't put the half, I just put minus, but because by the line, this is a fermion, okay? Straight lines are fermions, okay? If you want, okay, the first one I can put minus a half helicity, minus a half helicity. Let me try to find this amplitude. And with this condition and dimensional analysis, okay? That's the thing to go, okay? So because this is a minus a half, I know that has to be proportional at least to the spinor 3. And this is also spinor. This is also a minus a half helicity, okay, has to be also proportional to this guy. Give me the right transformation, okay? The angle has to be two angle spinors, okay? Or it could be that there are also 1 over the square spinor, okay? This can be one option, proportional to this. I'm going slowly, or proportional to 1 over these guys. Okay, I have, okay, this guy is not contracted. I have to contract it by Lorentz invariant. Okay. This thing, this also transforming the proper way under that property, under the little group. Okay. So I have other, you see, to write this thing, I only have two options. I write them now, I have to do Lorentz invariant, I contract them on themselves, 3, 2. Okay, or, okay, this is the case A. The case B, I contracted the square spinors among themselves to make it Lorentz invariant. So I have option A and option B. Oh, sorry, I forgot to mention the other property of the 3PT. I went too fast, but probably. Yeah. Yes, I'm saying to fulfill the property, I can have these two options. Okay. This is first. Now the question second. So there are two constraints: dimensional analysis and this. Okay, and now everything has to go. Okay, I mean, all these constraints tell me that this has to be proportional to this or this. Okay, and now my point is going to be this has dimension 1. Okay, so this is the okay y, but this has dimension -1. Okay, so this cannot be. Okay, but my 3-point function has to have dimension of energy. Okay, dimension of energy 1. Okay. I only had two options, and dimensional analysis tell me that. Okay, I can characterize my first amplitude. Okay, simple amplitude corresponding to these spinors. Okay, as a 2, 3. With a coupling in front, I don't know. Okay, I call it you have a coupling. Okay. This is one of my building blocks. In the same way you write the first operator between Higgs and two fermions in the Lagrangian as operators. Okay, I got the first amplitude. This is the easiest. I got the first amplitude of two fermions and a scalar. Okay, it does not depend on lambda, has the right dimensions and the right little group transformation. Okay. And now this game is the one I have to continue for the other amplitudes. Okay, for more amplitudes. Okay, involving gauge boson of fermions or whatever. Okay. I jump over something that I will explain the next day because of the 3-point amplitude. Sorry. It has to do with momenta. Yeah. Sorry. I skip because we are already time. No, it's time. Yeah, because I was missing a page in the previous one. I skip. Oh, because it will take me. It always take me longer. Okay. Yeah, it has to do with the fact that if I go to real momenta, you can show that this cannot be written as this amplitude has to be 0. You go to real momenta. Okay, I skip it. Sorry, I'll explain the next day. Okay, explain the next day. Okay, it's the need to go to a complex momenta. Otherwise, this is important. Otherwise, I cannot define the 3PTs. Okay, so let me skip it for the next day. Yeah, each of them, yes, exactly. I simplify by looking one by one. Okay, each of them will give me this factor out. Any of them. Okay, so if I have another particle 2 here with helicity lambda 2, I will have a factor here with helicity lambda 2. So I can treat each particle, okay, independently, okay, with a factor that comes in. Yeah. So now yes, exactly. Yeah, with massive particle, the situation is even more complicated because there is no helicity. Helicity is not a good quantum number, okay, because it can change under Lorentz. Helicity cannot change under Lorentz, okay, transformation. And now you have to look for another quantum number that usually is the third component of the angular momentum. You have to go to some frame like a, okay, usually you define it by going to the frame where you can, the particles at rest, and now you look for other quantum numbers. Cannot be the helicity. It's not a good quantum number for characterizing the state, okay, because you say, okay, it has helicity like this, but you're in another Lorentz frame, you have helicity to change the sign. Okay? So it's not a good quantum number for massless particle, the helicity, yeah, sorry, this part is needed when you define your states in a quantum field theory. Massless states, yeah, I don't know how familiar you are to this. That's probably, we'll need an extra lesson also to explain a little bit this. How you characterize the states in the massless theory. I know that the coupling is proportional to this, but I don't know what, there is a proportionally constant that I don't know. The only thing I'm telling you, this amplitude is proportional to this. Depend on the spinors like this. That's the only thing I know. Okay? But I don't know the proportionally constant. So I put a proportionally constant and I call it Yukawa coupling. Okay? And this is the idea that I said. And now assume that these couplings are very small. Otherwise I know, okay, I'm talking about 3 level. Okay, so there was 2 expansion, okay, I mentioned the other day, there's the expansion that I'm doing in lambdas, and again the expansion on small couplings, okay? So all my amplitudes, okay, the formal limit, this coupling goes to 0 in some sense, okay? I'm taking the formal limit, the coupling goes to 0, and the formal limit, lambda goes to infinity, formally, okay? Not to 0, okay? So in this formal limit that lambda goes to 0, okay, now I will write my amplitudes, okay? This formal limit. Now, after that, we know lambda can be small, but not 0, otherwise it's very interesting, and now we can have loops. This is a secondary problem. Okay, so you can consider this, okay, formally, okay, I take lambda going to 0, lambda going to infinity, okay, and in this formal limit, okay, that's it. There is no quantum loops, no quantum corrections.